So, hey everyone. In these sessions, what I've sort of been doing is I've been getting everybody set up with the proper environment to do PCB design with like Altium and like all the different version control workflows we do first, and then I've been going through this document here, which outlines sort of a pretty sort of intuitive but I think necessary procedure for designing hardware. And then as I go through, I've just sort of been outlining sort of like practically what all this means and when you implement it yourself in Altium. And so I guess to start, I'll just give a brief overview of sort of what I mean by PCB design. So For PCB design, the Rocket team uses Altium, which is an EDA, electronic design assistant. And What Altium does is essentially you have two forms of data input. You have your schematic files and you have your layout files. Um, your schematic files look something like this. They contain two very important entities, which are your components and your nets. Um, you can sort of connect components up to one another by connecting pins to nets. What Altium does, which is super useful, is it maps a component and its pins onto a certain layout of copper. So for example, this component here is a component with 24 pins on it, and each one of these pins is, in this case, mapped to one little section of copper along this footprint here. Um, And yeah, you can connect these pins up to each other using nets. So let's say I want to connect uh, this pin of this resistor to this pin of this IC, integrated circuit IC. I'll just create a wire from this resistor to this net here. So essentially what this does is this tells Altium that there's supposed to be a piece of copper connecting this piece of copper and this piece of copper. And how you actually implement that will be done when you push it to a layout file. And so once you've drawn all of your schematics, and I'll kind of go through the process of sort of how you start to think about a design, how you select your components, how you sort of draw your schematics, how you simulate them. And then once you've done all of that, then you can move it onto a layout. So when you initially push these files to a layout, you'll see something like this, where they're all sort of dumped onto the side of your PCB, which is this little black board here. And then you can move around your components uh, according to the rat's nest. So you can see here, there's a bunch of lines connecting these pads here. This is basically Altium mapping your schematic connections onto your layout. So it's telling you what pins are connected to what. It's just going to compute minimum distances between pieces of copper and other pieces of copper that should be connected to them. And so let's say I want to place these diodes next to each other here because this placement is pretty optimized. I'll just go ahead and route this piece of copper there. You can see here that the line between them sort of becomes at the end of this piece of copper, and then I can just sort of connect them up like that. And now when I manufacture my, well, if I were to create this, you can see here that there's now a piece of copper going in between these two things here. And so eventually, once you've placed all of your components and you've routed them with pieces of copper, this is in this case for this board, this was sort of what I ended up with as the placement and routing. And so you can see here all of the parts are sort of connected to each other as they should be. And Yeah, and there's other aspects to this as well, like yeah, there's a whole bunch of other features which I'll try to cover as much as I can today, but I'll keep it, to 2 hours. So there's obviously a bunch more detail to add. Yeah.
How long do you go from nothing to this, approximately?
Um, I was chewing on this design for about, so I went from, this was like my thing for the entire winter break last year.
Okay, so it pretty much, yeah, okay, a whole week of work.
Yeah, like I did very little else.
Okay.
Like I mean, obviously I saw family and whatnot, but like this was it was very focused on this.
Very, okay. It's
Yeah,
a lot of hours.
yeah, yeah. If Yeah, I mean, if you want to sort of optimize everything, in this case, this is the actual size of the board. So this was meant to go on very like space constrained assemblies, and so it was very important to me that it was as small as possible. And so that's what I optimized for. You can optimize for yeah the size basically. You can optimize for a lot of different things depending on your sort of design, where it fits in the system, and what it's actually functionally meant to do. Which yeah is kind of the point of going through this design process is to determine what you should be focusing on. And so now that everybody has sort of let's say like intuition to start with, um, I will go through and talk about sort of an electronics design process. So how do you go from nothing to that? Um, and I'll try to keep this general, so as to sort of not go into the weeds about too many topics in particular, because it's going to be a lot of information. But I'll, I think it's all pretty useful, and I try to map these to sort of like actual implementations in Altium. Um, so before I get started with this, does everybody have their laptop here? And if you do, I would highly recommend um, that you start downloading Altium now. I'm gonna try to get everyone set up with the environment so that we can all follow along with this.
Is it later? It's like a Windows thing.
Was that?
Is it Mac OS friendly?
It's a Windows thing.
Yeah, I'm not on my PC at home. So.
Okay. Yep.
What? Did you solder the pins by hand?
Uh, in this case, this was like I sampled this.
Oh.
So we like with solder paste, and then yeah. Have you done like SMD soldering before?
No, but I know how it.
Yeah, okay. But yeah. Yeah, it'd be a very tall task to hand solder like a QFN IC here. So
The link for how do you
yeah, so if you go to the drive, there's a document called TRAINING-ECSE-02 Altium Designer. That's in the management trainings folder. And there's a link for the download page there. Um, when you download it, you can create an account with your McGill email address, like is in the document here. And yeah, and just I think I've sent you an invite to join the Altium 365 workspace. So once you make an account, you should be able to join there.
Where'd say the the link for download was in the router?
It's just there's a little hyperlink.
No, but what?
Oh,
You sent it by email.
oh yeah, the invite link for the workspace is there, but if you want to get the download, you can go to this document and just follow the steps there. You can also just look up Altium downloads. It's probably like the first or second field that's going to come up. When you're registered for an account, you can access your profile, and you're going to want to select under My Organizations, under like Join Organization, America's McGill University Rocket Team. So the start, so Yeah, so I just ran through before sort of the general process of PCB design, and so I hope now you guys will have sort of at least the handle and the terminology that I'll be using as I go through this document, sort of an introduction. But this, I've essentially loosely followed a similar process in all of like uh, like I've had several years of experience with this stuff, and so I've followed roughly this process, and I figured I would sort of write it down in sort of a relatively formal way, and present it to you guys as sort of an introduction for how this maybe should go if you do things sort of in a structured and yeah way. And so the first step is going to be to generate your sort of design proposal. So, well, I'll take a step back. So the reason why we design electronics on the team is, well, like, and, the obvious reason is because a lot of us are like in computer, electrical, or even software engineering, and it's just good experience to have. Um, but uh, but also the Rocket team can't avoid designing our own hardware because there's some like various applications that like commercial off-the-shelf or COTS is the acronym devices don't meet. Like so many of our assemblies are super small, need to fit in confined and inaccessible places. Many of them maybe have very high temperature and pressure sort of data acquisition specs that they need to meet. Uh, maybe you're handling like energetic devices and you need remote arming and safing capabilities, or you need like remote operational capabilities. So you need to design electronics to make things safer in that way. Uh, and maybe you need to just stay inside a budget, and so you want to design your own thing instead of buying some other thing where you're paying for like the IP and then for somebody's profit margin. And so anyway, so for whatever reason you want to design electronics hardware, which I think is very cool. And yeah, so this is essentially just a process to how to go from nothing to something in your hand that works. So yeah, so the first step in this process is going to be to understand the design problem that you've been given. So maybe your lead, or maybe a sub-team leader, maybe even you yourself have thought about something that might be good to implement or necessary to implement. Um, and yeah, first step is to just think about the design problem. Write everything you know about the problem down in some sort of documentation. This is going to be super useful for you sort of going forward. And this should be done before you really think about any solutions, or like really just sort of understand the problem. Because, if you become attached to a solution and then you understand another thing about the problem and you have to sort of give up on it, and it might be hard once you're attached to it, or once you put effort into it. So just make sure you sort of do this first. Another useful thing is to use diagram software. I like to use draw.io because it's free and it's easy to use. I'm faster at this than I am at like hand drawing diagrams at this point. And I like to just create like sort of a few, like a set of diagrams that sort of show how my system is going to interface with other systems. So for example, this was a design that I did last year, and I just kind of like drew in a diagram that I had in the drive somewhere, what other electronic systems I would interface with, and like what would be part of those interfaces. And yeah, you could also include like sensors and electromechanical devices and maybe like a wireless link, and other parameters that you think are sort of important in terms of understanding the problem. Then I would highly recommend, even though it might be tedious, to write some sort of a requirements list. These can be in the form of functional and technical requirements. So just, yeah, functional requirements, just sort of like what should your device be doing at the end of the day. And then these are sort of to understand the design problem. They're not really, maybe you'll reference them in the future when you're designing your circuitry, but your technical requirements are going to be super important in both the component selection and the layout phases of your design. And so you're going to really want to flesh these out super well when you do that. And so, yeah, I can't understate the importance of this. I know it might seem tedious and it might seem pretty unrelated to what you're doing, but it's super important that you take time on this. I recommend taking like a week to understand the design problem and flesh out your requirements. Obviously, this will differ based on the complexity of your design. But yeah, that's like it's a super important step. And after you've done this, I think it's important to have a discussion with somebody about your design, with somebody who might know, have a little bit more context than you about the broader system. So, like whether that's your sub team lead or your project lead, or if you're an OCS, like a division director, um, or me, a technical director. Like, it'd be it's like I think it's super important to have a discussion with somebody, and even if they don't really agree that your design is necessary, you can still move forward with it if you yourself still believe it's necessary. But it's just important to get other opinions before you start spending a lot of time on implementation. Um, yeah. And so if you're missing any requirements or any of your requirements are incorrect, those will be caught. If you have thought about any design trade-offs, and you've missed some, those might be thought about by another person. Or if your ideas that you initially thought of are pretty inefficient and there are other ways to do it, you might discuss those as well. There's a lot of reasons to go through this sort of initial phase before you actually do any schematic implementation or layout implementation. Yeah, so at this point, you're going to start your PCB project. So if everyone can open Altium if you have it. Yeah. Yeah, see open. Yeah. What's your name again?
Abdel.
No, okay, nice. Yeah.
Wait, can you accepting my license once again
Okay.
and make sure that like off the license. Okay.
I ran into this with somebody yesterday, and all it took was just resending it and canceling it. But I think because you started a free trial, it might be more difficult. So we'll figure this out between me, you, and Graham. We can figure this problem out. Yeah.
Where's the document?
It's in the Google Drive. Everybody have access to the Google Drive?
Yeah.
Okay, it's 2025, 2026 management and trainings.
And
Yeah, it's just TRAINING-ECSE-01 electronics hardware.
yeah. Yeah, you're on.
Okay, so if everyone wants to open Altium and you can see if you're using a license, I think you can open Project Sophie, but you can't create one with a developed license. So you can just follow along when I open another project. But yeah, so if you want to create a new project, you can just go to File, New Project. When you click on this, a window like this will open up. You want to be in the location McGill University Rocket Team, because that's our workspace. That's where all our component database is. That's where the component database is. That's where our projects database is. And that's how you can access the version control for Altium as well. So it's super important that you're in the McGill University Rocket Team. You can name it just like something PCB project and your name, let's say. Oh, hit enter by accident. Anyways, didn't mean to do that. Okay, I will just do this again. There's a couple of other things I wanted to show. When you're creating a new project, oftentimes people just create them in the top level directory of the repository. And this is kind of annoying because then I have to move them later myself. So just make sure when you create a project, you put it in the right folder. To do this, you go in the advanced drop-down menu and you hit like in this folder field here, this is the folder that you'll be in remotely. And so just you can access all of the projects. If you want to open a drop-down, just hit the arrow next to it. Yeah. So
Can you change the default repository?
So can you change the default one?
Like just to not always have to go through the files and choose.
That's a good question.
You
You probably can. I don't know how to.
okay, I'll check.
Yeah. But yeah, so just make sure you put it in a good place there. So you'll end up with something like this. If you're I mean, I recommend you follow along on your own computer if you have it. And so just add, in this case, I'm going to add 3 schematics to the project. I'm going to explain why in just a sec. But yeah, you can just right click, add new to project.
Which folder is that?
Okay, so you've created your project, so that's good.
That's I opened a project in the
Oh, okay. So you should create a new project. So file, new project, and then it's going to open that window, and then you can just, if you want to create your project, you should unselect version control. So yeah, it's not taking up space in there, and then you can name it something with your name. Okay, so when you're starting your project, it can often be sort of a daunting task to do. Like you might have thoughts in your head about what you want to implement, and you might have like diagrams and requirements and all that, but at the end of the day, you're kind of starting from nothing. And so the first thing that I like to do is sort of structure my schematics in the project. How to do this properly, I think, is to use hierarchical design in Altium. So this basically means creating a top level sheet with subsheets abstracted down, and then defining their connections in between each other. So as an example, this is sort of what I mean. So you have like hierarchical schematic sets here where you have the top level schematic, and then you have ones that go down, and then you can define all of your connections in between sheets in this way. So I'm going to show just how to configure that. So you have your project with 3 sheets in it. You can just go and add a sheet symbol. And then you can just do that twice. So now you have these 2 boxes. You can link them to a child sheet by hitting properties. So if you go to the panels page, you'll have a bunch of different panels you can open, whether that's like components or Explorer. And in this case, the properties panel you want to open. And yeah, you can link these sheets to a subsheet in your design. So maybe link one of them to one of them, and yeah, the other to the other.
Why do you have 2 sheets?
You can just right click here, hit add new to project, and then you can add another
Schematic.
So you need to, yeah, exactly.
Breakdown. I did
Yeah.
my own.
And that's what I do to but then I created my product. You know, project is here, but
Yeah, that's good.
it doesn't open my double
I
click.
mean, there's nothing in the project.
That's just right. Okay, so it's not supposed to show the blank page with the schematic.
Well, that's only after you add a schematic to it.
Okay.
So you got to right click there.
You have your little squares drawn on schematic 1.5 or
Yeah, I mean,
which one we choose?
you just pick a top level sheet and then just add the add the sheet symbols to that.
How do you add the sheet symbol?
There's a tool in the top bar here. It's just this green one here.
Oh.
There's also keyboard shortcuts for all of this stuff. So if you look in Altium, you'll see like oftentimes you'll have a underline under a letter. So if you hit that letter, it'll open that menu. So for example, for the place, I could place a sheet symbol by doing the keybind PS, and then it will open a sheet symbol. This is you know, this is how you get faster with the software, is using these keybinds here. But yeah, that's a side note. Once you have this, I would go to one of the lower sheets, and I would add a port. So if you hit place and then port, so PR, you can do that. When it's still not placed yet, you can hit tab and sort of define its name. So let's say I want to have an input port and then an output port. And for the output port, we'll define the IO type as output.
How do you add like, I didn't see what you did to add an input or output ports.
So just if you open the place menu, and then you can open the port menu.
How do you open the place menu?
You can either go up here and select place with your mouse, or you can hit the key P on your keyboard. There's also a top bar with all of this stuff. What's the port code? So when you're placing ports, you should go to one of your lower level sheets. So one of the ones that's yeah.
These are all inside the region.
Yeah, exactly. Yeah, and then while you're placing them, you hit tab. Well, that's okay. So just do PR, you can place another one. So while you're placing them, you can hit tab and open its properties here, and then you can add a name. I think I put a tab there, so.
Oh, yeah.
How do you put sheets to the lower another one? I don't mind like this.
So you've got to access in your top level sheet. So when its properties and you can file these. Oh, I see. Oh, it's your computer. Very nice. What is it?
Zephyrus G14. Right, this is.
And yeah, so once you have two ports in your lower level sheet, you can go to the top level sheet and right click on the symbol that is associated with the one that has the ports, and you can right click on that, and you can select sheet symbol actions. And there's a option here to synchronize sheet entries and ports. So you can select that, and it's going to open sort of an option to find all your ports. You can select them both, and you can just hit add sheet entries. And it's going to give you an option to place them there, and then hit close. And now you have your sub-circuit with the input and the output defined on your sheet there.
Can you map one input to multiple sheets?
What's that?
Like the lower sheet for like output for it?
Yeah.
Can you map that to like two green boxes?
So each of these, so if I want to create another sheet, I can actually duplicate this circuit. Is that what you're asking? I can create two copies of this circuit, but this input port is only associated with that.
Okay, so one input port only has another like in a link to one circuit.
So this port here is only on this circuit, and the only way to access it is on this sheet symbol.
Okay.
If you had every project in like one top level thing, which I don't recommend doing, then the ports actually just port across to all the different sheets. So for example, in this person's design here, if you have like a port here, this port is accessible to all the other sheets in the design. But this is kind of unclear as to where things go. And so I'm just sort of introducing hierarchical design at the start, just so that everybody gets in a good habit of yeah, that sort of makes sense.
So one lower sheet, like in port, is gonna lead to one of these green boxes. That's
Yes.
it. Oh.
Yeah, exactly.
So how do you go to create another sub sheet for another case table? Say I want to just make one for this one.
You can open this properties by double clicking it, and then you can associate it with a file.
Oh,
And then you can link it to one of the files there. So that one's already linked to.
yeah, that's one
you
for
can
this one.
You can link two sheet boxes to the same file, and it will just duplicate the circuitry. So that's a very useful feature. Yeah, so I'll just mention this one other thing. I'll use this project, which is the backplane project that I've been using as the example in the document so far. It uses this hierarchical design in sort of a different way than I've presented previously, where you have essentially it's only implemented to make the drawing a little bit clearer. And also it's used here to repeat the same subcircuit twice in the same using the same like sheet. So you can see here I have implemented this linked document backplane v1.1 RPO schematic doc twice. And then by giving it a different designator for each one, so this one is URPO FC433, this one is URPO FC900. That means something in the design, but the designator isn't important. It actually creates two copies of every single component in this board. So, like for example, for Q17, it would just create a copy Q17 and then the designator of the sheet symbol. So two copies of it. So this is useful for design reuse, so that you don't have to redraw your schematics for the same if you happen to be implementing a very similar subcircuit twice. Yeah. So that's another motivation to do this. Let's see here. Okay, so now you've structured your schematic file, and you want to start actually implementing your design. So during this phase, so the first step in this is selecting your components. So during this phase, you should like reference your technical requirements a lot that you've created in your like requirements list here, because that's going to give you sort of insights into what specs you want to meet for your components. Yeah, to sort of select components, there's sort of many tools available online in terms of like learning what component specs mean. But once you sort of understand what the specs mean and you're looking for components, let's say, yeah, this is DigiKey. So if everyone wants to go to DigiKey on their browser, DigiKey is like a grocery store for electronic components. It's like a direct to consumer distributor, which is very nice. I think so and you can search for components in here. So let's say you have let's say you want to buy a resistor. So you just and you have a particular value in mind. So maybe you type in, if I can spell properly, resistors, and then you'd go, let's say you're looking for a surface mount chip resistor. So you just go select this topic here. And you can see here it's going to open this entire topic. DigiKey stocks over 1 million different types of surface mount chip resistors based on many different specs. Oops. So you can start to filter down the specs, based on what you've stated in your requirements and where the component needs to go in the circuit that you have in mind. Yeah, oftentimes this is a very sort of like back and forth process where you're sort of designing a circuit and then you realize that it has to meet a spec, and then you go into your component supplier and you find the component that meets the right spec. And yeah, so you can filter. Let's say you're looking for I'm gonna use a different example actually. Let's say, yeah, I'm gonna use a different example. Let's say you're looking for an N-channel MOSFET that meets a specific spec. So you look up N-channel MOSFET. Well, if I can spell. And you're looking for a single FET. So you just go find this category here, single FET. And you can see here it's again a big category before you filter it down. The first thing I usually do is just select for the stocking options here, just in stock. And then I don't really care about row HS compliance. Probably should, but and then for datasheet, yes, and then exclude marketplace products. Those are like the default ones I put in, and then you can then sort of select based on your spec. So let's say the most crucial spec to me, well, let's say this wouldn't happen, but let's say the only spec I really care about here is the maximum power dissipation, let's say, or how about continuous current? So I'm looking for a transistor that can handle 10 amps continuous from drain to source. And so let's say scroll down here, find around the value that I want. Let's say maybe I have a tolerance that it can go down to like 9.5 amps and maybe it should go up to like 15 amps, and then it becomes kind of ridiculous. And so let's just I can just filter that, find like the upper range, and just shift select there, and then it will filter all of those, and you can see it here, it filters down the quantities there. And so now I have a more sort of concise list to choose from. And yeah, so that's kind of a little bit about how to use DigiKey. But in terms of actually implementing components in your design, it's going to be really, really useful for you to leverage what we already have as MRT, because a lot of us actually use components with the same specs. And so for this, we have something called the Unified Inventory System. So if you guys want to go to the trainings folder and open TRAINING-ECSE-04 Unified Inventory System, I'm just going to go over this briefly. So Unified Inventory System is a inventory of electronic components that is integrated into Altium. The point of this is to abstract away from manufacturer part numbers and instead design around specs. And so this yields the following benefits. It gives us the ability to bulk order parts that the team can standardize on and use. It creates a standard set of symbols and footprints for the team to use. And it gives us less dependence on manufacturer part numbers. So let's say manufacturer part becomes obsolete, or maybe there's a cheaper one that becomes available. We're not sort of constantly using the same parts. We can sort of design around a spec instead of a particular part. And we can also have simplified cloud-based symbol and footprint dependency handling. So in this point, I'm just going to mention briefly, to understand how important this is, you will have had to design with Altium using local library dependency handling, where you have like schematic libraries and footprint libraries that you're sort of sharing with other team members, and you have like, you have to maintain them yourself and import them to various projects. And if you maybe copy paste a design from one project that doesn't have the dependency for the footprint and the symbol, it's gonna like not resolve it, and you're not gonna have a good time. Yes.
What's a footprint dependency?
Okay. I will. Yeah. Right. So how do you use UIS? You will have. So if you go to your design here, maybe go to the one of the lower level sheets. Oh, this is an old one. Okay, so you have your lower level sheet here. You want to implement a circuit. Let's say you have in mind you want to implement a reverse polarity protection circuit here. So you would go to UIS transistors. Okay, I'll take a step back. So in the Explorer panel, you can open the Explorer panel by hitting Panels. And there's a bunch of panels available. You can hit Explorer, and then you'll get a window like this to open up. At the bottom here, there's a folder structure called UIS. And in that folder structure, there's another one called UIS Components. In this, you have a variety of electronic components categorized into folders. Yeah. And so this is sort of how UIS looks in Altium. As per your question, what are symbols and footprints? So for each component, you have some. So this, if I click on edit, like one of the capacitor components, which as a general member you don't have the permission to. You have to be like added to a certain Altium group to have the access to that. But if you were to edit one of these, you'd see symbol and a footprint and various other parameters here and part choices. So essentially, why does cloud-based symbol and footprint sort of dependency handling? So what does that even mean, and why is it a benefit? Is the question. So essentially, these symbols can be stored on the cloud in like a folder like this, where somebody like goes and creates a bunch of symbols here for different components, and then links them onto the same sort of cloud platform onto a component here. The same goes for the footprints. And then internally in the component, Altium maps, so like maps this pin to this pad here, and then this pin to this pad. This was kind of what I was talking about at the beginning, where yeah, there's components, and each pin on the component is mapped to a piece of copper. So this red thing here is a piece of copper, yeah. So why is that beneficial over sort of having them be local? So in previous workflows before we used sort of this cloud-based like dependency handling, you would essentially have local copies of these two things in each of your PCB projects, and you would have to sort of like put them in manually for each PCB project, and maybe yeah, and maybe you'd have different ones for different projects. And then if you wanted to, let's say, reuse the design from one project in another project, you would have to make sure that sort of the dependencies for the footprints are and the symbols are sort of available so that they can be linked. And so that means just having like all of these files available. With this, it sort of automatically links them for every single component that's placed in every single file that's on the like cloud here. It automatically resolves the dependency. Does that make sense? Yeah. Okay, so how do you use okay, so I'll take a step back again. UIS is a catalog of components that the MRT uses that are categorized based on like a sort of a category code, and then a spec or like important parameter, and also they're like a package or size code. So for example, if I wanted to reference a 10 kilo ohm resistor that's in the 0603 size code in UIS, I would use the codified name res 10K 0603. And yeah, this is how and then this part has specific specs sort of associated with it that are outside of being associated with a particular manufacturer part number. So, like for example, this would be like the manufacturer part number. You can see you don't really like, I guess you can see here it's like 06, 03, and then FR 07, 10, 10K, whatever. Maybe you can tell it's a 10 kilo ohm resistor, but to me it's not obvious. So using the MRT part number kind of abstracts away from the part number, especially if we want to use a different type of resistor, because somebody looking at the design might not know that it's really important that we use specifically this resistor versus just any generic 10 kilo ohm resistor that meets these particular specs. In this case, there's a value spec, there's a size code spec, there's a tolerance spec, and there's a power dissipation spec. So to use this, if everyone can open Altium again, if I want to follow along, you can navigate to the UIS components folder, and you can see here. If I open UIS transistors, there's a list of transistors that we have in the MRT inventory. Let's say I want to place a P-channel MOSFET. So the code would be PMOS. It's okay for today if you don't know like what some of these devices that I'm gonna talk about are, but I'm just sort of showing, like, let's assume you sort of decided that you need this component as part of your circuit. You'll find it here, and you can right click on it, say place, and then it's going to open up this sort of menu. You can drag it around, you hit spacebar to rotate it, and you can hit X to mirror it on the X-axis and Y to mirror it. Well, sorry, X to mirror it on the Y-axis, I guess. And then yeah. So anyway,
What did you choose?
I chose TR PMOS SOT 23-3. So it's you. So you're gonna want to go to panels explore. If ever it says not connected here, just go and join. Just go and activate the or like join space. Yeah. Their panels explorer. UIS. UIS components. And then go to the transistors, and I was looking for here, and then I was for polarities. Actually, this one. And then you can go and right click this, save device, and you can okay. And so yeah, so I'm just gonna place that. We're also going to go to resistors. Let's say we want a 4.7 kilo ohm resistor. So we just, maybe it's in 0603. It'll find the relevant search. Well, you can put too much music. It'll find the relative thing. I should mention in the sort of in the like the standard way of representing a value with a decimal point in this is just to put the sort of like unit indicator where the decimal point would be. So in this case it's kilos, so you put the K yeah, so that's how you read that. And then let's say I also want to put this particular diode. Unfortunately, this isn't a UIS part yet. So it still has its manufacturer part number, but I use it in a lot of designs, and so I have it in there, but I need to actually abstract it away from this part number instead just like define a spec and with part choices, but I haven't done that yet. So anyway, so you can see this part number here. It's a BZT 58.5. And in this case, this is just a 13-volt Zener diode. And the point of this circuit is just to implement some sort of reverse polarity protection. And this Zener diode here just protects the potential between these two nodes here. And now I can, yeah. And so let's say for this simple subcircuit, these are all the components that I'm going to add. And now I can move on to wiring the schematic. Oh, actually, I'll just mention one more thing. So I've mentioned that you can use UIS for your component selection. It's really convenient for your own workflow. But you can also leverage this components catalog here, which is the components folder. You can go through this. This has sort of a lot of different components that are sort of like just randomly put in there. There's no like codification. I would verify that all of these are actually sort of like correct because they might not be. I haven't personally, yeah. Essentially, this is just sort of like an inventory of anything that anybody imports into Altium. Everybody has access to this folder. Everybody can edit it, but you can really trust that these components here are sort of associated with components that will be ordered in bulk for the team. Yeah, that's basically it. So just don't feel obligated to change your spec so that you stay within the spec of these components here. Like if you need to order a wacky component that isn't sort of part of this catalog, you can do that. Yeah. And don't feel sort of obligated to stay within the bounds of this. In terms of actually how to take a component from the manufacturer's, let's say you want to take a component off of DigiKey, the manufacturer will should provide sort of information on the package and the symbol. If you know that it's a package that is already sort of available on the cloud, you can just use the footprint that's on the cloud. I'm not going to go into depth in all this. I know maybe this won't make a lot of sense right now, but maybe you'll remember it as you're sort of going along, and you can always ask when you come to this. But just remember, if you need to add a component that isn't already included in the sort of UIS folder, you can absolutely do that. And you can use the models that are available to sort of do that. And if you have any questions, just reach out in the PCB Design and Altium channel. Anybody would be happy to help you out, including myself. Yeah. So let's say you're done selecting your components and you want to move to wiring your schematics. There's some like this is a pretty easy part of the process. Yeah, the important thing to note is just to keep things clear and keep things keep subcircuits separated, perhaps into their own sheets as I've shown. So to open like a wiring menu, you can just hit Control W and it'll open this crosshair menu thing here, and you can just place a wire and connect these two nets. There's a red X that appears there. When you've selected two pins, when a pin is going to be added to the net, it will show a red X that will indicate that the net will connect those two things there. And so these two pins are now part of the same net. And you can do the same for the gate of the PMOS and also the source. Connect to the port here, and then connect this Zener diode up here, like so. And now you can also place a ground symbol on the other pin of this resistor. So to do that, you can just hit PO, and then, well, you can just go up to this top menu here, for example. I'll use a different workflow, and you can just place a ground symbol as such. once you've done this, I'll give a little bit of time. It is the one.
Can you show the circuit again?
Yep.
I don't think, after it realized, I think I opened a. Yeah, so I wasn't able to open. anything. So, what's that?
Yeah, it's because of the license that you're. So now you have access to their space, right? But I'm going to try. Maybe it. Yeah.
I say after the.
Yeah.
I don't think it's worth it to bother him.
Yeah. But it's just yeah.
How did you flip the output cords?
Well, you can just connect it to you can connect actually either end and what do. So if you were to, let's say for whatever reason wire this end, you'll actually know that it's connected. And it will make that end be the or but honestly what I would do is just you actually haven't specified this position. It's just follow it as and add a ground symbol. You basically the important thing to note about ground symbols and power symbols and those is that they're actually accessible in every sheet of the schematic. They don't need to be ported. So that's one benefit of using them. It's also just clear for anybody reading your schematic, like that this net is special because it's ground. Yeah. So once that has been done, you can go to your top level sheet and actually define I'll just mention one other thing. You can see here that Altium has put these little red squiggles next to these pins here. Altium isn't smart. It can't tell you if your circuit is not going to work, but it can tell you about like really obvious stuff. In this case, it's really obvious that this pin actually only has one connection on it. And so that's sort of suspicious to Altium, and it's going to tell you, it's going to give you a warning like, hey, are you sure you want to have this pin have one, be the only pin on this net? And so that kind of makes sense.
I don't understand what you mean by like what does Altium say is wrong or like weird?
So because it's essentially warning me, so it says error nets with only one pin. It's essentially warning me that, okay, I've defined it to a port on this sheet, but this sheet actually hasn't connected this to anything. So if I go on the copper, that pin will not be like, there's nothing else to connect it to. And so let's say it's important that it be connected to something else for a circuit to work. Altium's going to tell me that's probably an issue. And in this case, it's just because I haven't finished the design yet, but it could help you catch like if you've like miswired something, or like you think you've connected it properly, but you haven't actually, or like it's misaligned with the grid. Does that kind of make sense?
I think it's just because I don't fully understand how like the ARX works, but it's fine. I think I'll figure it
Okay. Now I want to add a terminal block here as the connector, so I can just go to UAS in the connectors folder and just hit terminal. And in this case, I want to put a 3-pin terminal because I know that there's an input connection, an output connection, and a ground connection. And so yeah. So for this example, just add a terminal. And I will wire this port to here and this port to here. And then I will put a ground on the 3rd pin here. You can see here now that Altium removes this warning because there are now 2 pins connected to this net. There's the pin of the transistor here, and there's the pin of the connector out here. So you can imagine like this port here goes into this sheet. Does that kind of clarify?
Yeah. Okay, like Altium was like, there's nothing actually coming from the input.
Yeah.
Okay.
Yeah. But that's not quite it because you can see here it never actually gave me a warning for this one because there's two connections on it. But that doesn't mean that there isn't a problem. So that's what I mean, like Altium isn't smart, but it will tell you like super obvious things. Like there's only 1 pin on this net. That's gonna be an issue like 99% of the time.
Or first.
Oh, that's it. The diode. Also,
The other side.
from the other side, it was as if like the diode was acting as another like.
Yeah, exactly.
Yeah.
Altium doesn't know that neither of these pins are like sources of anything.
Yeah. Okay.
They can't
okay.
input any energy into this.
Okay.
Yeah.
Like it sees the diode as if it was another input.
Yeah, like it just sees, okay, there's 2 pins on this net. That could be it. That could be fine.
So I'm not
Yeah,
gonna
okay.
get it.
But if there's only 1 pin, Altium knows like, okay, that's probably not okay. But yeah, in that case, it wouldn't have been okay because there's nothing to really do from there. Just kind of that wouldn't be a good. But that's on the level of that's on the level that the engineer has to. Well, I guess not the engineer. The designer has to sort of consider. Okay, so let's say we've placed all our components here. Now we want to. You can see here there's like a little question mark next to it, and that's sort of by default. Yeah.
Where is where's the subsheet on this green port?
So the
Not port,
the
symbol.
So the subsheet is linked to this.
Yeah, but where physically? Like, are you worried about like how much you put on the subsheet to fit in this green symbol?
No. I mean, the subsheet is just to.
Let's say this is like way bigger of a design.
You could
You're not worried that it's not gonna fit on the.
You could add another subsheet and then create another schematic, like here, and then link that to there, and then you can make it. You could move down the hierarchy, like in my in this design here. And so in the top level sheet, you can see here in the AV arming circuits sheet here, I've then there's actually a lot of circuitry to include here, and so then I chose to abstract away these 4 circuits into subsheets. As I mentioned previously, I reused one of the subsheets.
There's no actual physical representation of this circuit.
Not yet.
Not like right there.
Yeah, not yet.
It's just about fitting all your code.
Yeah.
All your code, just your design.
Yeah.
Yeah. Okay.
Organized. Exactly. Okay. So we've placed all our components. Now we got to, you can see here next to the designator, this is a question mark. By default, it shows a question mark, so you've got to annotate them. To do this, you can just open Tools, and then Annotation, and then Annotate Schematics. And you can open this menu here. It's going to show you all the designators in your design. You can hit Update Changes List. So hit TAA is the keybind. And then you can hit Update Changes List. Hit TAA. And then, so you can see here all your components here. Yeah, it's essentially you can see here like the underline for tools, and then tools has an annotation, so that's A, and then annotate schematics and another A. So that's where that you can hit update changes list, so it will tell you that it's making 4 changes because you've added 4 components. And then if you hit OK, you then see your current designator is D question mark, and then your proposed designator is D1. And then you can agree with that, say accept changes, create your engineering change order, ECO, and yeah. Now you can see that it's proposing that it annotates all these objects, and you can say, that's good with me. And then close, and you can see here now all of your things are designated. In this case, actually, there's only one of each, like there's only Q1, D1, R1, but if you had like multiple R's, obviously.
Yeah, it's just a number your parts on your circuits. There's no like practical linkage between.
No, it is. It's linked by the designator. So when I go to actually I'm pretty close to I think you'll understand once I explain the layout. So I'll just yeah. Okay, so now I've designed this sub-circuit. In this case, I had this sub-circuit drawn because I want to explain that this is kind of used in this circuit here. So in this broader, this was again using the backplane board as an example. This circuit was used in this sort of part here, where this is reverse polarity protection on this little power path here. And so I want to confirm that this little subcircuit, only 3 components, actually does its job. And so how I would do this is I would take this subcircuit, and the best thing to do would be to actually build it. But if that's not possible, the next best thing to do is to simulate it in Spice. So Spice is a simulation software. It's as old as time. Yeah, and so it was actually made before there were graphical user interfaces. Now there are graphical user interfaces. This is called LT Spice. You can download it off the internet. It works on Windows and Mac. I'm not going to give an LT Spice tutorial here. So honestly, I'm not qualified to give an LT Spice tutorial, but well, I'm not qualified to give any tutorial, but I can kind of give you guys a start. But anyways, I'll kind of show yeah, so what is LT Spice? LT Spice essentially allows you to draw circuits and connect up components and simulate them using some simulation parameters here. Essentially, each one of these components has a model in Spice that each time it creates an instance of that model, and you can assign it different parameters. So in this case, I can assign this resistor like a resistance value and whatever. I can assign this transistor, various profiles. I can pick from ones they have available to assign a different profile to it. And yeah, the same goes for this diode here. Yeah, and then in this case, I want to run a DC sweep using this power supply here. And so yeah, essentially what I want to do is just start this power supply from 7 volts and take it to 30 volts and see how my circuit behaves. And so I just used this with a spice directive. In this case, the spice directive is .dc for DC sweep, and you can just look up how to use spice directives. Pretty like it's fine. And so if you hit run, you'll see this kind of simulation window, and you can probe different nets. So for example, well, this node here, you can see my DC sweep command worked because this node is taking from 7 volts to 30 volts. So that's great. But the thing that I wanted to test with this circuit is one thing in particular where I know that there's a certain spec of this PMOS that I want to verify my circuit actually protects. So I know that the potential across here for this PMOS cannot exceed 20 volts. And I'm thinking that, it's possible that somebody might apply more than 20 volts to the circuit for whatever reason, and I want to make sure that this device doesn't get damaged. And so the point of me simulating this is to see if I can make that happen. And so in this case, this Zener diode actually conducts in the reverse when it reaches its breakdown voltage. And so in this case, it was just over 13 volts for this particular diode. It's important to note that this diode is not the one that I'm going to buy, but it's actually just a representative model of the diode that I'm going to buy. So like if that makes sense, I couldn't find a spice model for the particular diode that I was going to buy. So I just used a representative one. And this is a technique you'll have to use often when simulating. And you'll sort of figure it as you go. Yeah. And so you can see here, okay, I've simulated the behavior of the circuit. I know that I can see here that just over 13 volts, the Zener diode breaks down, and actually this potential doesn't increase anymore after the breakdown of the Zener diode. So in this particular case, this subcircuit is going to work here. And then I can be confident in my implementation of the circuit here that, it's going to be fine. And there's obviously a lot more going on this PCB than I've simulated with that just one subcircuit. But like with my knowledge of the design, I can kind of know that, okay, if I simulate that subcircuit, there's probably nothing else on the board that's going to affect its behavior in any way that simulation will become invalid. Is that sort of so in that way you can sort of abstract you can abstract away everything else and just yeah. So that's a little bit about simulation. You can run simulations as large as you want, so you can simulate sort of very small subcircuits here. This simulation is like quite amazing to me. But this was done by a previous member who was a very good designer, and yeah, he made simulations that sort of encompassed a lot more of the design. So using various techniques to abstract away complexity, using like let's say for example step functions that depend on with like dependence on certain voltages reaching a certain level, and maybe you implement a time delay or something like that. Yeah, you can abstract away a lot of complexity just by doing stuff like this. For example, just by doing this, he abstracted away an entire integrated circuit that's called a high side NMOS driver just by implementing this function here. So that is to say, if you're trying to implement something that maybe uses a complex part, just think about functionally what it does and how you can abstract that away using like a simpler model, like just a voltage supply. If that makes sense. And so if you're using some clever techniques, you can sort of simulate a lot of stuff about your design and make sure everything is going to sort of work. So once you've finished drawing your schematics and selecting your components and running any simulations you want to do, you can then have a schematic review. So again, you should post this in PCB Design and Altium, which is a Slack channel you should definitely join. Yeah, essentially the point of this schematic review is before you start any sort of like PCB layout or whatever, you should run it by somebody who has a little bit more knowledge or context about the rocket team, and catch like inappropriate component selection or net connection or other wiring issues with simulation, or concerns with the results, or any other implementation issues that should be fixed before the design is advanced to layout. I've reviewed enough designs where somebody just throws at me like schematic and a layout all together, and I find an issue with like something like something simple with the schematic but requires a lot of work to re-implement in the layout. And so doing this in sort of a staged way allows you to not redo as much work when it inevitably, something inevitably comes up in the review that you have to redo. And so yeah. And so this might take a couple of cycles, it might take some back and forth. But eventually once you're ready to advance to the layout stage, you can do so. So yeah. So as I sort of showed right at the beginning of this, when you have your design, you can have two input data files. You can have your schematic files, you can have your PCB file. So if you want to go to your project and add new to project PCB, you can do that. And it's just going to open a blank file here. So there's three things I would do before I start any sort of component placement or routing, which is just to set up the document, which involves defining sort of a board outline. So you have like rough dimensions based on some sort of a requirement from a mechanical person, and you would put that on there, and you would define your design rules so that Altium knows sort of what to warn you about. And you'd also define something called your layer stackup. So I'll go through those three things just because I think they're important, and it will save you time in figuring this out if I go through them now. And so to define your board shape, what I would do is go to panels, go to view configuration. And here you can see all of the layers in your design. So you have you have many different types of layers. Here you can see you have like copper layers where you actually make your connections with the copper in your PCB. You have your overlay layers, which is this like the white text on the top here. It's called the overlay. Top and bottom overlay. You have your paste layer, which is for something called a solder paste stencil. And you also have your solder mask layer, which shows the openings of the soldering mask of the solder mask. The solder mask is this green part here, and the openings are any part where it becomes like silver. And so the openings you can solder to, if there's a pad there. There's other layers as well. So what needs to happen here is you need to add a mechanical layer and just specify it to type board. And hit OK. And so now you can see you added another mechanical layer. My Zoom thing is hiding this menu here. Okay, sure. Then on this bottom part here, you can see you have like a list of layers that you can access. Just you can tab through them if you want. And just make sure that you have board selected here. And then you can go ahead and place a board outline. So to do that, you can just place a rectangle. So hit P to open the place menu, and then press rectangle. So you can specify the layer type as board here. And then you can call it like board shape or something. So now you can place a rectangle there, make sure it's selected. So to select something, you have different options. You can just hold down on your mouse, or I guess if you're using a trackpad, I recommend you get a mouse. I don't have a mouse here, but yeah. You have two different selection windows. So if you drag down to the right, you can create a blue selection window. As you can see here, this doesn't select this object if it's not fully in, but as soon as it's fully in, it selects it. And then if you drag up from the bottom right, you can see it just selects anything that's only partially in there. And then you can define a board shape from board outline. So if you go to design menu, and then board shape, so S, and then define board shape from selected objects, so D, and then you can see it reduces your it reduces your board to that sort of shape there. So go here. So place and rectangle. Okay, so make sure you're on your board layer here. And then you can place a rectangle. That. And then you hit escape to exit the tool. Yeah, and then it's already selected, so you can select it again if you choose. And then you can go to the design menu. Stop here. And then you can go to board shape. And then define from selected objects. So you define that shape actually on your copper layer, so I would probably not recommend that. But you can move it to your board shape layer by going into its properties and choosing a different layer. So let's move it to the board one. Board is near the top, right? So you're drawing a polygon. That's well, that's not now. But if you want to place a rectangle, you can escape to exit out of the tool there. And then you can go to the place menu. So yeah, either hit there, you hit P, and then you can just open rectangle there. You can draw a rectangle. So now it's red, so you can see it's on the top layer, but you can actually go to it into its properties and change its layer to forward if you've created forward layer. So if you go to okay, so we'll take a step back. You can open the view configuration panel. It's at the bottom. And then you can see you have all your layers, off the layers, whatever. You can right click somewhere on there, anywhere, and you can say add mechanical layers. And then you specify the type board. And then hit open. Now you can see you added another layer there. And now you can select your object there and you can open its properties. Board layer. And then you can select this object. So using the selection tool, you can sort of drag here, select it, and then you can go to the design menu. So you can hit D, and then you can go to the board shape menu by hitting S, and then D again. And so now you have you've got to select it first, and then you can. Yep, that's great. Okay, so that's board shape, and then you can define your you can define your stack up. So if you go to DK, okay, design and then layer stack manager. So now it opens a window like this. You can see here, you have sort of different colored layers. These represent the layers that you'll see in every single PCB. So you'll have, a solder mask layer, you'll have copper layers, and then you'll have some sort of a dielectric layer. In this design in particular, there are 4 copper layers. So I'm just going to select one of the copper layers and hit add. And then I'm going to make sure the count is 1, make sure it's a signal layer, and then OK. And then you can see here it adds 2 more layers. I can name these like, whatever. I'm not going to go through and name every single one of them, but yeah. So what is a stack up and why is it important? So a stack up is important when you are routing stuff that might need particular characteristic impedance. So I'm not going to really go into sort of the weeds of that, but essentially for various designs, it might be important for you to to control impedance of your design. And so this is just, and Altium has backend tools to facilitate you designing around a sort of controlled impedance stackup. And so if you define your stackup in a particular way, it will actually communicate. Altium will allow you to design as if you had the proper sort of setup there. And yeah, to determine, to determine the values that you should put in your stackup, you can go to the manufacturer page. So the manufacturer we use is JLC PCB. So if you go to your browser and just type in JLC PCB, and in this case, I'm looking for the stackups, so I'll just type stackups, and I'll select go to the controlled impedance stackups page. Just PCB and stackups. And you can see here, they have sort of different values, different stackups here, with different dielectrics. And in order to make sure Altium knows what stackup you want to eventually use in your design, you should just grab the stackup that you're going to use, the values here, like the thickness, the dielectric constant of the material that's inside, and then you can import that into your layer stack manager. And then eventually the point of this is so that you can define impedance profiles for routing. So let's say you want to route, for example, a trace that's like a single-ended microscript, and you want to reference it to the ground plane on layer 2, and you want to route it on layer 1, for example. You can define its target characteristic impedance and whatnot, and use the stack up to route it in a particular way that it has that impedance. And this is defined by the distance from the this is defined by its capacitance and its inductance, and so you can define those by changing its thickness and its distance from the plane below it, and also its length. But yeah, so you can also define many different types of impedance controlled traces. If you've taken like any transmission line type courses, you'll know about like single-ended coplanar waveguides, so you can match to that as well. There's a lot of different things you can do when you have provided a proper stackup, and so this is why this step is important. And so now you can just save that if you're done, and go back to your PCB document. And the last thing to do to set up your document here is to define your design rules. So design rules are how you tell Altium what's a problem. Yeah, as sort of a demonstration, I'll just go to I'll just go to this project here, and I will move around a component according that sort of violates a design rule. And you can see Altium sort of warns me that I'm violating a design rule here. So in this particular case, a couple of them are being violated. There's some short circuit constraints. There's a distance constraint here, and there's a distance constraint between the two components, and also these two pieces of copper here. Altium basically tells me, okay, there's a violation in the design rules that you told me where you're not supposed to short these two traces, and yet you are, and these components are too close together. And so it's going to tell me with these, green X's that there's a problem here. And so then it'd be the responsibility of me to fix it. And so this is important to set up. So if you go to your own design, you go to your own design and you open the design menu and then go to the rules menu, you can open up all your design rules. You can see there's many different categories of design rules, whether that be clearance or width or many other categories. Luckily, somebody has already there's a lot of people on the team who have been designing PCBs, and so there's a lot of people who have put in the proper rules into their designs. I have you can import these rules from other designs. So in this case, if you want to have a place to start, you can just go to the drive where the trainings were, and there's a folder called Training-ECSE Hardware Workshop, and I just have a design rule file, which is this file called PCIe backplane v1.1.rul. And if you import this just by right-clicking anywhere on this side menu here, saying import rules, and then you can select all and find your .rul file. This will actually configure all your design rules according to that .rul file. And if that person has gone through the JLC PCB manufacturing capabilities and put them in properly, then that design rule file will be quite useful, sort of for your to let Altium know what's sort of improper in your design. Yeah. So any questions about design rules?
There's only one set of rules?
So you
Like, what if you were to design another set of rules?
Yeah.
Would you just put that on the drive and someone else could use it, or is it too?
Yeah, you can totally define your own design rules. So let's say you wanted to let's say you wanted to define like a routing width rule that was different. You can just let's say you want to route up to 100 mil on the top layer. You can just define like that, go save it, apply. And now that's going to be the design rule in your design.
But that set of rules in the drive is good for what?
That's just sort of a baseline for you to get
Just the
started with.
default, yeah, okay.
Yeah,
That makes sense.
yeah, I mean,
Because you could, I mean, if you were to upload every single different rules, right? So
Yeah.
that would.
yeah, and there are like yeah, exactly.
Okay, and not one set of rules works for every, or like most components, like every component has a different set, or
So rules are for the PCB, like
sorry,
entirely.
the piece you're trying to build together.
So yeah, no, like oftentimes you'll need to specify particular rules
Okay, sorry.
for other designs. This is why it's important to know how to navigate this field. But if you want somewhere to start, you can always import design rules. You can also open up a design that on the Explorer and export its design rules. So to do that, you can go to just the Explorer, open up a project. Let's say you trust your project lead's project for its design rules. So you can go to, say you're on FC Hardware and you trust Graham's design rules. You can go to Flight Computer and I don't know, maybe like hit GPS module here. And then you can go open up this file. So Open. And then you can go. The design rules menu is actually only accessible when you have the PCB document open, which makes sense. And then you can go and open the design rules menu just by going to the design menu and then rules. And then you can go and see here, okay, he's added like various rules for routing. And you can just export these rules. And you can just choose to export all of them if you want. And then you can that's some. And then you can import them into your own design. So you don't need to use the one on the drive. You can use any but yeah, I just figured I'd show you the import and exporting because I learned that like 2 years into using.
Yeah, I figure. I imagine a lot of components rules work when you're trying to design a new model from a previous one. But
Yeah. Okay, so I've been quite slow today, so it's already 5, but if you guys still have time, I have about probably like 15 minutes more of stuff to say.
Sure.
So yeah. Okay, so once you've sort of configured your document, you need to go and save it locally so that for the next step in the process. So once you have your PCB document configured and your schematics drawn and everything sort of all your designators annotated and everything, you can then import your schematics to your PCB document. So to do this, just open the design menu in a PCB file, in a schematic file. So that's important to note is that the design, all these menus will be different depending on if you're in a schematic or a PCB file. So you just have to be aware of that. So you just have to go design and then update PCB document, and then it will find a PCB document in your file. And it's going to tell you every single component you have in the design, where it's going to go, and maybe all the nets in the design where they're going to go. And then you can just hit execute changes. And it will show you like, if it's good, if it's done. And you can see now that all the parts are just sort of thrown there to the side. You can see that there are little lines connecting the pads. And so these are defined by your schematic, where sort of you define, okay, a certain pin is on a certain net. And so it will show you the minimum distance between one pin on that net and another pin, which is super useful for component placement. So the first thing you want to do when you import them is you want to sort of organize the placement into subcircuits, where sort of, yeah, you try to optimize the length of the lines in the rat's nest. So in this case, let's say, I don't know, there's no real right answer to any of this, but you honestly just have to do it in a way that makes sense. And so, for example, in this case, this makes a lot of sense to me, where I have like, I've minimized it so these don't cross so much. And yeah. If I were actually sort of to make, I see that these two rat lines cross here. And so if it's possible, I might actually choose to switch the connections on this on these two pins on the connector. But I'm not going to do that for today. I'll just sort of make it work. And then to route, yeah. So let's say I'm happy with my component placement. Component placement is a super important part of the process, and it will make your life so much easier if you spend a lot of time on this part of the process. Because yeah, if you optimize the length between everything that needs to be connected to everything else, routing will just be super quick. Is everybody any questions on this part?
How would you actually implement on an actual PCB board the crossing of the two connections?
So yeah, so let's say it wasn't possible for me to let's say it wasn't possible for me to switch these on the connector, which I would just go in my schematic and actually flip these two pins. So I would go like, okay, net D1 is actually connected to pin 1 and net P1 is connected to pin 2. But if let's say that weren't possible, I would just figure out a way to route this in a way that like worked. So for example, I could go like this here, and then I could do this up here, where I go around and do that.
So any crossing requires like big detours.
There's no crossovers.
Well, there's no crossing between
Yeah,
the-
you could also use something like a via. So I could go like this here, and then I could, while I'm routing this, I could hit tab and then switch this to layer 2, sorry, or to another layer.
Okay.
So in this case, it's a 4-layer stack up, so I can
Cross under.
I can move to the bottom layer. It's going to create a via, so that's this hole here, and then you can see it's now blue here, and I can route on the bottom here.
Yeah.
And if I isolate this to the layer that I'm currently on, it will only show me the copper that's on this layer. So for example, the blue is on the bottom layer, and then the red is on the top layer here.
Okay.
And then for the rest of this routing, it's super simple. Just go like that. For the ground plane, what I'll choose to do is actually, for the ground connections, what I'll choose to do is implement a ground plane. So to do that, I can make a polygon pour. That's just a section of copper. So just place polygon pour. It's going to open a menu here. Well, it's going to open like crosshairs here. I can just sort of draw something. You can always modify the shape of it later. There's a lot of tools online, documentation for how to use polygons. But yeah, so you can see it gives you something like this. Right now, there's no nets connected to it. In real life, this is a solid pour of copper. So all of this stuff is copper. All this sort of lighter green stuff here is copper. This darker green stuff is just like solder mask with no copper on it underneath it. So I can assign this to a net. So what I'll do, I can either assign a net from the drop down here, so I can just write in GND if I know what it's called, or I can go to this little dips, like the dropper here, and select ground here, and then you can see it kind of looks funky, and that's because I need to re-pour it. And so to do that, I would just go right click it and go to polygon actions and then re-pour all, or I could re-pour violating polygons. I could re-pour, there's a lot of re-pouring options. And now you see I've re-poured it, and two things, like these things, the connecting to the pads that weren't there before are now there. That's because it's found all of the pads that are connected to the ground net, and it has connected them to the pour. And so now these two pins are actually electrically connected because all of this is copper. But you can see here that these nets are isolated because they're supposed to be isolated. So so why would you choose to do a polygon pour instead of just routing? Well, there are many reasons why you might choose to do this. The first being for sort of your your own routing convenience, let's say. Or maybe you're implementing some circuit that needs to handle a lot of current. So you want to make it run through this entire block. So in this case, I've actually set the opacity of the polygons to less. So that's why they're sort of see-through. But you can see here that these pads are all connected, and when sort of like this entire pore fills up with current, and that allows it to sort of handle more than it would otherwise if I just routed a small trace. But yeah, another good reason to use polygons is to sort of put more ground in the, sort of have ground more accessible everywhere, let's say, because in general, a good rule of thumb is that ground is your best friend when you're designing mixed signal PCBs, which is kind of a simple, like mixed signal PCBs is kind of a simple general way of describing PCB design when if you're not doing like high frequency stuff or analog stuff or something like that. But yeah. Yep.
You just recall what's the ground?
So in electric circuits, everything needs a reference. So you have like voltages, signals flying around, and you need to sort of reference them to something. We refer to ground in PCB design as like the 0 volt reference. If you're working with power systems, ground will actually be a stick that you shove in the ground and dispel charge into.
Okay.
So like for example, on this power supply here, there's like a black terminal and then there's a green terminal. The black terminal is like your 0 volts, and then your positive terminal is whatever voltage you apply. And then this ground here is the chassis, and it's connected to the grounding lug on the input connector. Yeah, so I mean there's two ways of that's like the two sort of grounds. There's the 0 volts, which is like when you're signal ground, I guess, and then there's like if you're working with like mains power systems, you have your ground.
So if there were no ground,
Your earth
basically,
ground.
there would just be an accumulation of electricity, like
Yeah, it would be undefined
is that
behavior.
okay.
Yeah, like you wouldn't improper grounding is like it's something that people run into a lot, and you just can't predict what's gonna happen.
Okay. Okay.
Yeah.
Okay. It's just
Like it's undefined behavior just because circuits don't work without a reference. So that's why ground is your best friend. Yeah. I'll just quickly show how to set the opacity of these. So if you want to set the polygons to be like more transparent, you can just go to the view configuration options and then increase the transparency here. And then yeah. And so now you can go to the 3D view by hitting 3. And you can see here that you kind of can see all your copper and where it's not copper. And you can see all your components here, and you can see your board outline. And there you have your little PCB. So that's kind of that's it for routing. I'll just briefly mention that you might choose, depending on your design, you might choose to simulate your design. You can do this in a couple of different software. I'm not going to go over it in any sort of detail. I'll just mention it today so that you know it exists. There's Keysight Power Integrity Analyzer, which is sort of integrated with Altium. There's references to it in this document here. So there's Power Analyzer by Keysight. There is also ANSYS. You can export your PCB and do some simulations in ANSYS. So if you want to do like signal integrity simulations or something like that. Again, I'm not going to go into any detail. I'm just sort of letting you know that it's an option to simulate your designs if sort of there's something that either you or your reviewer might have flagged that will be important to simulate. Like for example, if you're doing something very high current and you want to simulate the power path, that would be a good idea. Yeah. So at the end of this process, you have a PCB, you have like the full thing. If you want to export it and get it manufactured, you could. But at this point, you'll want to post a PCB design review, so a layout review in PCB Design and Altium, the Slack channel. You can ask me or your sub-team lead or project lead or like OCS division director to give you the review. and essentially this will like catch a lot of different things. Like there's so many different things you could catch in this process for like a complicated design. And so, this process could take you like quite a long time. Like for this design, I had somebody that's super knowledgeable or more knowledgeable than me, in PCB design, and we went for like I think a week back and forth, and just sort of like he's suggested things and I fixed them, and then he suggested more things and I fixed them. And then eventually it was ready to sort of be manufactured. Um, and yeah, so just I cannot stress the importance of sort of giving your reviewer ample time to review as well. Because like, if you're like crunching up against a deadline and you're asking your reviewer to review your design and you have like 2 days to do it, that's really not a good position to put a reviewer in. And yeah, so just make sure if you follow this process, you're sort of giving ample time for everything to happen. Yep.
How would you review your own?
How would you review your own?
Well, by yourself
That's a great question.
before.
You could right. Yes, I forgot to mention. So on a sort of one thing that's really great to do is to again look at other designs in the past, see what they're doing, see if there's anything that you're doing that's like not great. You could also look at other design reviews. So if you look in the Slack channel, PCB design at Altium, there's always going to be other design reviews that are posted. These design reviews are also saved to the saved to the Google Drive. Where's PCB design at Altium? Yeah. Yeah, so like somebody will post reviews here, and you can sort of get a review. Oftentimes they'll be in the form of like a PowerPoint. And so will be a review here. Well,
Okay, a review is like not just one comment, it's like the whole.
yeah, and then you'll post a path like, yeah, exactly.
Okay.
It's a whole thing.
Yeah. It's not.
So
Are there people assigned to the review, or it's just anyone? I mean, anyone.
well, like I'm planning on sort of putting out a Google form for like anybody on this channel that might want to do reviews, and so then I'll make that list available to you guys. But yeah, you can like at me, or you can at your project lead or sub team lead or something, and they'll give
I was wondering, is there like a challenge or something where you can like ask for reviews for like personal projects just to like see if you can like practice or something?
yeah, I mean you can post them in this.
Okay.
Yeah.
Even if it's not relevant.
Yeah, whatever.
Okay.
Yeah.
Let's see.
Just if it's not like Rocket Team related and not a tight timeline, just say just like at your
Oh, yeah.
convenience or something
Yeah,
like
yeah.
that. Not like ASAP. Yeah.
That's nice.
Yeah. Yeah, for sure. Go ahead and do your own personal projects like with Altium. It's here just to learn. And anyways, so at the end of the process, let's say okay, I forgot to answer your question fully. So how do you review your own design? You can look at past reviews, you can look at past designs, and just sort of get a sense for what people are going to say. Because like if your reviewer is anything like me, I have the same talking points that I say for like all of the reviews, and maybe there are specific things that I like, find on a review that find on the board that's like different, but oftentimes people run into the same pitfalls, and so you could find other reviews. The last thing to do is to export your manufacturing files. So to do that, you can just follow, there's a link here, JLC PCB Altium export settings. So you can see here, you can just configure the export settings there. You can add a output job file. So if you go into your PCB project, add new to project, output job file, it will open this sort of a window where you can add a fabrication output. For us, you want to add a Gerber files and NC drill files. So I'll just go ahead and do that. Gerber files, NC drill files. And you can configure them like so, and you can just see that JLC PCB has offered the configurations that you should have. So just sort of configure them, hit apply, and then configure the drill files, and then hit OK. And then you can go ahead and export them into your local storage. And then you're done, basically. You generate content and you have manufacturing files. People send them in orders PCB as like zip files. So like say Graham wants to order 10 ST links, which is the name of the board. Then he gives me a zip file that yeah has the drill files and the gripper files in it. Yeah. And that's pretty much it. And again, the manufacturer is called JLC PCB. So if you want any of their information, you can just go find their website. And yeah. So that's all I had for today in terms of the like presentation slash tutorial thing. Are there any other questions or?
Are you gonna post this recording?
Yeah, yeah, I'm gonna post a recording. If it's like, yeah, I might edit it down a little bit just to like make sure so that people don't have to sit through me like not talking for like 10 minutes because I'm helping with something. But yeah, I'll post the recording.
In Slack?
Yeah, in the trainings channel.
Yeah.
Yeah,
okay.
the one that you signed up on.
Sounds
Yeah.
good.
Yep.
Cool. Thanks a lot.
No worries. Thanks for your interest, guys.
It's okay, we just message
Yeah,
directly or?
you can message me directly. You can message
know.
and yeah,
Okay, no, you don't mind?
yeah, I don't mind. You can also
So if you can.
I might,
message them directly.
might also recommend you like post in a public channel and at me so that
Of course,
people
yeah.
can
Yeah.
people can also
course.
benefit from your question. Because chances are many people have the
But
same
for
question
one
as
question, it would be, or maybe wait some multiple questions if I would, actually, I guess.
well, I mean, anytime.
Just creating a post in a channel for just one question.
Well, that's fine.
I mean,
Why Sophie?
it's all about not annoying.
We'll
Yeah.
see if it's appropriate.
Yeah.
Yeah, it's fine. Yeah, it's good. Like you can post any question you have in the PCB Design and Altium channel. Just like don't add channel.